Dear viewers, welcome to all. Today in this module we are discussing synthesis of nanomaterials. That is, we are outlooking various synthetic strategies employed for the preparation of nanomaterials. Regarding the synthesis of nanomaterials, there are two important approaches. These two approaches are the top-down approach and the bottom-up approach. In the top-down approach, we begin from a bulk material and convert it into nano-level substance. Whereas, in the bottom-up approach, we begin from the atomic level and assemble that atoms. Finally, we are getting nano-level systems. Regarding the top-down approach, as I mentioned, nanomaterials are synthesized by breaking down of bulk solids into nano-sized particles. It is based on the principle of dispersion. The starting material must be in the solid state. That is, for the top-down approach, we have to begin from solid materials. Then this picture simply illustrates the top-down approach. In the left side, there is a bulk material. First of all, it is fragmented into some components, and finally that fragments are changed to nanoscale structures. Now, bottom-up approach. Here, nanomaterials are synthesized by assembling atoms or molecules together. Here, the important peculiarity is that the starting material is either in gaseous state or in liquid state. That is, here we can use solid state materials. Now, this picture is simply illustrate the bottom-up approach. Here we begin with the atoms. Atoms then changed it to clusters. Clusters finally converted it to nanoscale structures. These two synthetic approaches, what we mentioned, the top-down approach and the bottom-up approach, are collectively represented in this figure. The bulk material, powdered it, then changed it to nanoparticles. In the opposite approach, that is the bottom-up approach, atoms assembled together to get bigger atoms or clusters, and that clusters changed it to nanoparticles. See, the presence of the nanoparticles are exactly at the middle. Now, we have to discuss with the various top-down methods. We can have a glimpse on various top-down methods. What are the popular top-down methods? There are enormous number of top-down methods, and some important methods we are discussing here are RF plasma method. RF stands for radio frequency, RF plasma method, then thermolysis, mechanical grinding, laser ablation, and nanolithography. In this presentation, we are discussing all these methods somewhat in more detail. Now, the first method, that is RF plasma method. RF, I mentioned, radio frequency. It is one of the oldest technique, especially used for the preparation of metal nanoparticles. We are very much familiar with the metal nanoparticles. Nanoparticles of silver, gold, other metals can be prepared by this RF plasma method. And this RF plasma method involves vaporization of a bulk metal and its condensation on a suitable substrate. Metal is placed in a container in an evacuated chamber. It is then heated by using high voltage radio frequency coils. Regarding the experimentation, the experimental setup is shown here. In this, there are two RF coils, and the metal is placed in between the RF coils. There is a collector rod. There is an associated vacuum pump is there. Helium gas is also supplemented during the synthesis. During the RF plasma process, the metal vapor nucleates on helium gas ions. That is, nucleation happens on the surface of the helium gas ions. These particles, after the formation of the nanoparticles, diffuse towards the colder collector rod, which is already mentioned in the picture, colder collector rod, and deposit as final nanoparticles. The reactive nanoparticles, the obtained nanoparticles are highly reactive, and that nanoparticles are passivated, that is made them inert by introducing almost reactive gases like oxygen. That is, oxygen gas is used for the passivation of the reactive product nanoparticles. Next top down approach is thermolysis. Thermolysis, as the name indicate, thermo means temperature, lysis means fission. Here the decomposition of solid, that is the starting material or the bulk material, takes place at a high temperature. This method is also, as in the previous method, used for the preparation of metal nanoparticles. The solid should contain metal cations and molecular anions or metal organic compounds. The instrumentation of thermolysis is shown here. There is a furnace, vacuum gauge, molecular pump, evacuated quartz tube is also here. The material is placed in an evacuated quartz tube and heated up to a desired temperature and allowed to decompose. The obtained nanoparticles are finally passivated by suitable gas like oxygen. Next top down method is mechanical grinding. Mechanical grinding or attrition or milling is a top down procedure. We all are familiar with the grinder, which is an instrument used to powder materials. This mechanical grinding is a popular method due to its simplicity and relatively inexpensive nature of the material. It is used in the synthesis of different type of nanomaterials. One important aspect is that we can prepare metal nanoparticles, silica nanoparticles, different type of nanomaterials based on mechanical grinding procedure. Regarding the experimental part, mechanical grinding is illustrated in this picture. Here there are two refractory balls shown in this picture. Many balls can be added, and these high energy steel balls rotating with different speeds, and the starting material, that is the bulk material, is placed in between these refractory or steel balls. As a result of the rotation of the steel balls or these refractory balls, bulk material converted to fine powders, and the powders then converted to nanoparticles of desired size. It should be noted that in the case of mechanical grinding, energy is transferred to the powder from the balls, from the high energy steel balls or refractory balls, and this energy transfer depends on some important parameters. These parameters are rotational speed, size and number of the balls, the time of milling, and the milling atmosphere. Nanoparticles are produced by the shear action during grinding. Now we are discussing next top down method, that is laser ablation. High energy laser beam is used to chisel out nano level substrate from a bulk material. Laser beam is used as the primary excitation source of ablation for generating the nanoparticles directly from solid materials. Here the substance, the bulk material, must be in the solid state. Nanoparticles are produced during the condensation of a plasma formed by laser ablation of the bulk material. This picture illustrates laser ablation procedure. A laser beam which is focused on the substance, and in this chamber there is a plasma pump is there. The target is placed here. There is associated solution, As a result of the ablation, bulk material is converted to nano level substance and dispersed in the solvents. The solvent may be water or organic solvents, and this laser ablation procedure need not stabilizing agents. Next top down approach is the nanolithography. This word nanolithography came from three parts. They are nano, which simply represents dwarf, lith means stone, and graphy means writing. That is, dwarf or tiny writing onto stone is the word meaning of the term nanolithography. In general, in nanolithography, we start with bulk solid and nano-sized patterns are then developed on it by removing unwanted or chisel out unwanted parts from that bulk material. Nanolithography generally use a mask containing a particular pattern to be written on a substrate, and it is irradiated by using suitable radiation or electron beam. The substrate will be covered with a resist. A resist has a pivotal role in nanolithography. This resist facilitates interaction of the beam, either photon beam or electron beam, with the substrate. The resist control the size of the nanoparticle to be obtained by this procedure. Now, there are different type of nanolithography. Some important nanolithographic methods are electron beam lithography, simply represented as EBL, then photolithography, nano imprint lithography, and so on. Several methods are also there. These are the important nanolithographic procedures. Now, the first one, electron beam lithography. As the name indicate, we are using high energy electron beam instead of photon. The sample is first covered with the electron sensitive resist. I already mentioned about the term resist. The resist is then subjected to electron beam exposure. As a result of the electron beam exposure, some chemical development happens and some portion is removed. After that, metal is allowed to deposit and lift off excess metal, and finally we will get the nanostructure depends on the electron beam exposure to the resist. After the exposure, the excess part of the metal is removed by some methods. EBL is highly useful to fabricate two-dimensional photonic crystals, quantum wells, quantum wires, and quantum dots. That is, EBL can be used to prepare different kind of nanomaterials based on their structure. Then the next lithographic procedure, nanolithographic procedure, is photolithography. Photo means the word came from photon. That is, the photolithography, we are using light and optical mask to light sensitive photoresist on the substrate, and the picture simply illustrates the photolithographic procedure. And UV light, there is a photoresist. The photoresist is placed on wafer. Wafer simply means the substrate. The positive photoresist is removed after UV irradiation, whereas if the photoresist is negative one, it will retain after developing. That is, the photoresist may be either positive photoresist or negative photoresist. Both will ultimately lead to the formation of nano-sized materials by using high energy photons. Now, nano imprint lithography, or simply NIL is the acronym. NIL involves a template stamp pressed against a deformable imprint resist layer deposited on a substrate. Here there is a polymer resist substrate, and we are pressed down the stamp, and the resist formation at controlled temperature and pressure occurs, and finally After the removal of the stamp, we will get desired patterns, and using this desired patterns, we will get nanoparticles of desired size and shape. We are discussing the advantages of top-down approaches, and we learned several top-down procedures, and let us check what are the advantages of the top-down approach. Here, large scale production is possible. Deposition over large substrate is possible by this approach. Generally, chemical purification is not required. That is, the obtained nanoparticles by the top-down approach almost pure. No need for further purification. Then, regarding the disadvantages of the top-down approach, the size distribution is broad. That is, 10 to 1000 nanometer is the size distribution. Particle size may differ by shape or geometry. Then defect or imperfections may be introduced. Expensive technique. The procedure is not cost effective. Then another aspect of today's discussion is bottom up methods. Bottom up method, as we already aware, we begin from atomic level substance and assembled together to get nano-sized materials. And the popular bottom up methods, there are enormous number of bottom up methods, and today's discussion we are selecting this important bottom up methods: chemical reduction method, chemical vapor deposition, sol gel synthesis, hydrothermal synthesis, co-precipitation. These all are popular bottom up methods. Regarding the first bottom up method, that is chemical reduction. Chemical reduction method is very common method for the synthesis of nanoparticles. Especially, it is highly applicable for the synthesis of colloidal particles of silver, gold, copper, platinum, etc. by the reduction of their metal salt precursors in solution. Then what are the common reducing agents selected? The common reducing agents are sodium borohydrate or their derivatives, and the reduction is happening generally under cold conditions in the presence of ice to yield nanoparticles of desired size. Then the chemical reduction procedure for the preparation of silver nanoparticle is achieved by AgNO3 is reduced by using sodium borohydride under colder conditions. Nanoparticles of molybdenum can be obtained by the reduction of molybdenum trichloride solution using NaBeT3H, that is triethyl sodium borohydride. By this reaction, MoCl3 get reduced to molybdenum. Here molybdenum is in +3 oxidation state, and it is get reduced to molybdenum to 0 state, and the reducing agent performed in this reaction is NaBeT3H. Next bottom up approach is the chemical vapor deposition, or simply CVD. CVD is a method to produce high purity, high performance solid state nanomaterials. It involves the formation of the nanomaterials from the gas phase at elevated temperature, usually on to a substrate or catalyst. During the process, the substrate assembly called the wafer is exposed to one or more volatile precursors which react and decompose on the substrate or catalyst. This illustrates the chemical vapor deposition setup. There is a source material which is mixed with the carrier gas. A wafer or the substrate is placed at the middle of the chamber. This is the reaction chamber. After the reaction, there is gas exhaust is there. Heater is there. This heater can provide decide or set temperature to the system. A laser beam or plasma can be used to enhance the reaction. Volatile byproducts obtained during the process, which will exhaust out, can be removed by flowing gas through the chamber. This is another bottom-up approach. This is the most popular bottom-up approach called sol-gel synthesis. The sol-gel process is a wet chemical technique. Wet chemical technique means we can use solvents, water, alcohol, organic solvents, etc. And in this procedure, a sol, that is a colloidal solution, is converted to an integrated network of nanoparticles, that is gel. Metal alkoxides and metal chlorides are generally used as the precursors. For example, silica nanoparticles can be prepared from tetraethyl orthosilicate, that is a metal alkoxide, and these precursors undergo hydrolysis and polycondensation reaction to form a colloidal system. That system assembled and finally converted to a gel phase. Sol-gel synthesis. There are different steps accompanying the sol-gel synthesis. What are the various steps regarding the sol-gel synthesis? They are formation of stable solution of the precursor or the salt solution like alkoxide, chloride, etc. Then gelation, aging of the gel, which is otherwise called syneresis. Then drying of the gel, dehydration of the gel, and densification and decomposition of the gel. Sol-gel synthesis is simply illustrated in this picture. Precursor solution is there, hydrolysis is carried out, gel formation occurs, and then as we mentioned earlier, consecutive steps are happening, and finally we will get nanoparticles of desired size. Hydrothermal synthesis is another important bottom-up approach. Hydrothermal synthesis, however, needs the presence of a special instrumentation. That instrument is called hydrothermal autoclave. The process happens at high vapor pressure level using high temperature aqueous solution. Hence the name hydro for water, thermal for temperature, hence the name hydrothermal synthesis. Hydrothermal synthesis is illustrated here. This autoclave consists of bursting disc, stainless steel lid, there is a Teflon cap, water or other solvent can be placed inside the autoclave. After the reaction, reactants will react at a high temperature, and the heating temperature is definitely above the boiling point of the solvent. We will get nanoparticles of desired size. Another important bottom-up method is the co-precipitation method. Co-precipitation means precipitation together. Here, the required metal cations taken as soluble salt are co-precipitated from a common solution medium. Usually, the precursors are hydroxides, carbonates, oxalate or citrates. The precipitate obtained after drying is heated to the required temperature in appropriate atmosphere to get the final product. Co-precipitation method is very simple method for the preparation of nano powders, that is nanoparticles in the powdered form. Ionoxide nanoparticle, which is very popular method for the ionoxide nanoparticle, that is ionoxide nanoparticles can be prepared by the co-precipitation of Fe2 plus ferrous ion and ferric ion in a basic medium. This basic medium is provided by generally ammonia solution like that, and here this reaction illustrates co-precipitation of Fe2 plus and Fe3 plus ions to get iron oxide, that is Fe3O for nanoparticle. One of the drawbacks of this method is the difficulty in controlling the particle size and morphology. That is, we will get particles of different size and different shape. Now, let us enter into the important advantages of the bottom-up approach. The advantages include ultra-fine nanoparticle formation, very small size distribution, that is, we can prepare particles in the size range of 1 to 20 nanometer, but it is very high in the case of top-down approach. This bottom-up approach is cost effective compared to top-down approach. And regarding the disadvantages of bottom-up approach, some disadvantages are large scale production is very difficult, chemical purification is essential. But remember the point that in the case of top-down approach, chemical purification is not necessary. And the two type of synthetic approaches we discussed today are the top-down approach and the bottom-up approach. Top-down mentioned earlier, bulk converted to nano, and bottom-up approach, small particles converted to nano. That all about this presentation. Thank you all.